Hello and welcome to another walkthrough. Now this time it will be on Further Math FP2 paper 4A in the UK syllabus for the 2024 paper. I would say this is quite a tough paper, so let's see how it goes. Are you ready? Question 1. Use Fermat's little theorem to determine the least positive residue of 21 to the power of 80 modulo 23. Right. So in Fermat little theorem, we know that if we have a to the p, we can put that to equivalent to a, and this is a modulo p, where p is a prime number and a can be any integer, right? So for example, here we have a to be 21, so I can put 21 to the power of some prime number, and because 23 is also a prime number, so I'm going to put 23 here, equivalent to the same base, 21. But we put here modulus, I can just write mod, mod 23, right? Just according to the theorem there. Now, we're going to find the least positive residue. It's just like finding the remainder, basically, of 21 to the power of 80. We have here that it is 21 to the power of 23 is equivalent to 21. So basically, if we want to find the remainder of 21 to the power of 23, we can just find the remainder of 21 modulus 23, right? So that means, now if we power this, right, so how do we make it 80? Well, because if we, so how do we make that 80? So we need 23 2 times, or actually 3 times. Yeah, so 80 equals 23 times 3, and that would make 69, and then if we add 11, we're going to get 80, right? So the reason why I did this, because so that I know what to power 21 to the power of 23. So if I put that to the power of 3, yeah, and then multiply it with 21 to the power of 11 here, so all this will become 21 to the power, all of this will be 21 to the power of 80, which is what we want. But that is the left-hand side, so we want to do the same to the right-hand side, right? So that is also 21 to the power of 3, yeah? And also times 21 to the power of 11, right? Because this is the modulus property here. Yeah, it's the properties of modular arithmetics, yeah? So now we're going to find the right-hand side instead. So that's mod 23. Yeah, so we keep going with the right-hand side because now we simplify the thing there from 21 to the 80 to something simpler. Now, how do we do this, right? So if we combine the power there, right, so I'm just going to put them together as 21 to the power of 14, yeah, mod 23. And then this will be 3 to the power of 14 times 7 to the power of 14 mod 23, right? I think I'm going to split 3 to the power of 14 to 3 to the power of 3. Yeah? How many times do we need? 4 times. And times 3 to the power of 2. Yeah, because when I put that to 3 to the power of 3 because it becomes 27. And now we know that if we do 27 mod 23, that's going to give us equivalent of 4. Yeah, we can replace that with 4. It's just basically simplifying, keep simplifying the thing here, yeah. And then, well, 7 to the 14, right? If we do 49, yeah, okay. So if we do 49 instead, so that's 7 to the 2 and all to the power of 7. Yeah, that's going to simplify the thing. So you will see what I mean here. Just bear with me. Don't forget to do mod 23 here because they're all equivalent there. So, right, so we find the remainder from dividing 27, which is 3 to the power of 3, by 23. What is the remainder there? The remainder is 4, right? So the remainder of that term would become 4. Yeah? So it's 4 to the 4 instead. All right, 4 to the 4 instead. And this will just be 9, right? So I'm just going to keep it as 9 for the time being. Now, this one, 49, if you divide 49 by 23, you get remainder 3, because that would make it 49 divided by 23, so you have 2. So 23 times 2 is 46, and then remainder is 3. So it's just 3, which is the remainder, to the power of 3 instead. Yeah, that's modular arithmetic. And what can we do next? We got to keep going here. This is also 27 to the power of, wait, all this together, right? 3 to the power of 2, so that's 3 to the power of 9. So that's 3 to the 3 to the power of 3, isn't it? Because you have 3 to the 2 here, and when you combine these two, you have 3 to the 9. And 3 to the 9 is 3 to the 3 to the power of 3, right? It's just this, yeah? And let's see this one. So how do I put that one? How about I make it, well, if I multiply all this, what do I get? It's just 256, right? So that's not hard, yeah, because that's not a big number there. We can just divide 256 by 23 already there. So what do we get there? So we have to do some working here. 256 is equal to 23 times what? 10, right? Can we do 11? Yeah, we can do 11, right? So if we do 23 times 11, it would be 253. So that's remainder 3 there. Yeah, so this is 3 then. Multiply. Well, that's again the same thing. 27 here. 27. If you divide 27 by 23, you get remainder 4. So that's just going to be remainder 4 to the 3 again, right? So I'm just going to keep going here. Yeah, so the least residue. We got to keep going. So that's, yeah, I'm just going to multiply all this, yeah? So that's 4 to the 3 times 3. So how do we make it? So this is 192, and that's all mod 23, right? I'm just going to leave it there. Yeah, like the mod thing. And then, so is that 5 or 6 or 7 or 8? I'm going to do 8, 23 times 8. Yeah, that's the closest. So that's just, yeah. So that's just mod. What's the remainder there? It's 8, right? So there you go. The least residue, which is the least remainder that you can get. So the answer is just 8 mod 23 here. And we can say, we can conclude here that this is 21 to the 80 equivalent to 8 mod 23. And that is just the final answer there. So basically just keep going with the, modular arithmetics here, the rules. Similar to algebra, you just have to keep using this, right? Mod, yeah? So that's number 2 done. So what do we have here? Number 2, determine a closed form for the recurrent system u1 equals 4, u2 equals 6. So those are just the conditions. And then we have here un plus 2 equals 6, un plus 1 minus 9 un. So this is basically a linear recurrent system, right? So it's a linear recurrent system, so this is going to be similar to solving a second order differential equation in the FP1, yeah? So if you make everything on the same side, I have un plus 2 minus 6 un plus 1 plus 9 un equals 0. Just make one side 0 there, just like when you solve the auxiliary equation in second order differential equation. And then this is the second term, i.e. the second order. This is the first order, this is the 0th order, yeah? So you can put like m squared minus 6m plus 9, just the same way you would do in second ODE. And then factorizing this would give you m minus 3 squared equals 0, right? Now, but when we put the general solution after solving this, right, and this is a repeated root, so we're going to put un equals, again, the same as the second ODE, a plus b, but the variable here is not going to be x now, it's going to be n, right? So this is going to be a plus bn times, now the 3 here as a root, right, will be used as the base of the exponent here, and 3 to the power of n, like that. Yeah? Okay? Now, because we are given also that u1 is 4, so 4 equals, you putting n, you got to put n as 1 here. So this is a plus b 3 to the 1. And b times 1 is b, right? Okay, and that's the first equation there. And the second equation where we have u2 equals 6, right? So that's 6 equals the same here, a plus, but that is 2b. And this is 3 to the power of 2, which is 9, right? Yeah. And so you solve this equation. Seems like I can... So if I do the first equation, multiply the first equation by 3, right? So if I multiply the first equation by 3, I'm going to get 12 equals, and expand everything at once, 9a plus 9b, right? And for the second equation, if I expand also, I have 9a plus 18b here. If I subtract them, I'm going to get rid of a, so I have 6 here equals, that's minus 9b. That means b equals minus 2 over 3, right? Yeah. So that a would be equal to, let's use that one. So the first one, 4 over 3, I move 3 down there, and then I subtract b, so I'm going to get plus 2 over 3 there. Yep. So that's going to be 2 for the a. And I think we solved it, right? So that's a and b. So if we write the sequence there, so it's going to be un equals 2 plus minus, yeah, 2 over 3 n 3 to the power of n, just like that. Yeah. Okay, so let's go to the next question, number 3. Okay, what do we have here? Use the Euclidean algorithm to determine the highest common factor h of 2, 3, 4 and 96, right? So I prefer doing it this way, yeah. So you can, I don't know, this is easier, but when you write, maybe you got to follow the template, but this is just a quick way to do it. So we're going to use 96 to divide 2, 3, 4 first. So what do we get? 96, so that's, I think that's about 2, right? So 96 times 2, we get that. Subtract 2, 3, 4, that's remainder 42. So I'm going to write here 2. So 2 is the quotient, yeah? And when you do 2, you're going to get, what's that again? 42. 192. And when you subtract, you get 42 here. Yeah, and then you're going to use this remainder to divide 96. So that's also 2 times, right? 2 times, I write 2 here, so this is 84 instead. And I subtract that, I get 12, right? Yeah, and then we keep going. Yeah, we keep going. So we do, just not going to write the line here. So you're going to have to divide 42 by 12. And that's about 3 times. Yeah, I write 3 here. So you get 36, you write 36 minus, and then what's this? This is 6, right? And then you keep going. Now 6 divide 12, you get 2 now, and the remainder is 0. So the last divisor is 6. That means 6 is the answer. Yeah, so the highest common factor is 6. Now, I'm not sure if this is okay, but you need to write it, so you're going to have to write. So if we wind back, yeah, if we kind of like reverse engineer all this column thing that I do, so it's just 2, 3, 4 equals, what was that? 96 times, this is the first one, right? Times 2, and the remainder is 42, yeah? And then we're going to use 42 to divide 96. So 96 equals 42 times 2 plus 12, like that, yeah? And then what do we do? Hang on. 42, 12, 12. Yeah, okay. So we use 12 to 12 will go here to divide 42, right? So 42 is 3 times, and then the remainder 6. And then we got to show the last line that when we divide 12, we get this, and remainder is 0. So this one is the answer there. Okay, just like that. Maybe it's part B. Hence determine integers a and b such that we get that form. And don't forget that h is still the highest common factor. So if we start from the end, trace back, it's like backward substitution here. So we start from this line where we have, so 6 is the subject then maybe, 42 minus 3 times 12, yeah? So just move 3 times 12 to the left, to the other side. And then because we, at the end, we want 96 and 2, 3, 4, so we got to keep going with this. For example, we can substitute 12 as something else, yeah? So 12 was also actually 96 minus 2 times 42, right? So I'm just going to write that. 3 times 96 minus 2 times 42, right? That. This is just algebra. So you treat 42, 96, just like x and y, maybe, yeah? And we're not going to touch anything with 6 because we want 6 on one side. So we're just going to derive the other side here. So if we expand that all out, we get minus 3 times 96 here and plus 6 times 42, right? Look at them as separate terms, right? Don't multiply anything out, yeah? If we collect the term, we see that we have 142 and 6 42s there. So they're going to be merged to 7 times 42 minus 3 times 96. Now it seems like we already have the 96 there, so we don't need to touch it. We just think, okay, how are we going to substitute 42 there, right? So if you look at here, you can see also that we can take 42 from this line because 42 is 2, 3, 4 minus 2 times 96, yeah? So you're going to have 7 brackets, I'm going to sub 2, 3, 4 minus 2 times 96, right? Like that. And everything else is just the same. Yeah, and we keep going with that. So we have, so 7 times 2, 3, 4. So that seems to be simplified already. And here we have minus 14 times 96 minus 3 times 96. So if we merge all the term, yeah, I think we got it. So I'm just going to write as they want there. So this is just 2, 3, 4 times 7 plus 96 times b. So that is 96 times, isn't that minus 17, yeah? Equals 6 there. So that's probably it. Part C. Solve the congruence equation 96x equivalent to 36 modulo 2, 3, 4. All right, so it's going to take some steps here. First, according to the theorem, you need to find the GCD. Well, I think we already got the GCD here. So if GCD of 96, which is the left-hand side there, and 2, 3, 4 is not 1, then we need to divide by the GCD. And we got from part A, using Euclidean algorithm, that it was 6, right? So that means we're going to have to divide everything, yeah, by 6. So we get 16 for 96. 36 divided by 6, we get 6. And the modulo there, 2, 3, 4 divided by 6, we get 6, 3, 18, and then we get 54, so that's 39. All right, so the congruence equation becomes 16x equivalent to 6 modulo 2, 3, 4. No, we have to divide that as well, so we get 39. All right, now from this part, you need to, I mean, if you want to solve for x, right? It's just like algebra here, almost like you want to solve for x. But to do that, you need to find some inverse of 16 here, that when you multiply both sides by some number, so let's say it's k, so you multiply by k, it's going to give you, so we are finding some number, 16 times k, it's going to give you the equivalent of 1 and the same modulo here, 39. Yeah, we are finding this guy here. So we are finding the guy k, so that when we multiply 16, then the whole thing become equivalent to 1 modulus 39. All right. Now we could look back in part D, right? So we need to get 39 and 16 in the picture here, yeah, because we need to find the inverse of 16 modulus 39. So if you take this one, right, I'm going to take that one and just do something about it. Okay. If you divide across by 6, right, because we already know that 2, 3, 4 divided by 6, I get 39. Yeah, there we go. We got 39 times 7 plus, that's going to be 16 there, minus 17, and this is going to be 1. Right. So, and if we apply modulus 39 in here, well, that's going to go to 0, right? Because we know that if we divide, split into 2 terms, the remainder of this will be 0, right? So that's 0 plus minus 17 times 16 equivalent to 1 here, modulo 39. Yeah. Now, we already get it. So do you see that 16k equivalent 1 here? This is also 16k equivalent 1, right? I'm going to add a page here. Yeah. So that means the inverse of 16 under modulo operation is going to be minus 17. But we don't want negative number. Yeah, we don't want negative number there. So what we're going to do is we're going to substitute that by a positive inverse here. We can do that by just adding the modulo here, 39. So we're going to get 22. So we can say that 22 is the inverse of 16 under modulo operation 39. So if we apply that inverse to the equivalent congruence equation there, we're going to have 16 times. So I'm going to multiply all the sides. This was x first, right? Yeah. Equivalent 6 times 22 modulo 39, right? Because again, we know now that the k was 22 and 16 times 22 will be equivalent to 1. So we can put this as 1, right, under modulo. So that's just x then. Equivalent to, that is 132 modulo 39. Yeah. And then if we find the actual remainder, so that's basically x is the least residual or the principal solution is just basically found by just dividing the thing. So 39, I think, times what? 39 times, I don't know, 5. Wait, hang on. That's too much. 4. That's also too much. 3. How about 4? Yeah, 3. Okay, so times 3. And then if you subtract that by 132, you get remainder of 15. Yeah, so that means the principal solution is 15. So we got the first one to be 15. Now how do we find the next one? Well, basically we just use a similar equation here, but remember it was 2, 3, 4 before, right? So that means the 15 is the least one, but it can go up as long as it's not exceeding 2, 3, 4. So in fact, the maximum one is the 2, 3, 3. It's just one less than the actual divisor here, 2, 3, 4, right? But how do we find that? Well, basically we're just going to do 2, 3, 4 equals 15 plus 39 times k. Wait, hang on. This should be x, yeah? So we just keep going, substituting k equals 0, 1, 2, 3. We already got the first one because when you sub 0 in, you get the principal solution. So if k is 1, then you get x to be, what's that? 39 plus 15, so that's 54, yeah? If k is 2, then you get 15 plus 78, so that's 93, right? If k equals 3, you know what I mean, right? So basically, you keep adding by 39. No, hang on. Not keep adding by 39. Yeah, keep adding by 39. Yeah, basically. So 93 plus 39, I get 132. plus 39, I get 171, plus 39, 39, I guess 210. Yeah, and that will be all of them. So that would just be all the answers. Let's conclude. So we have 15, 15, 54, 93, 132, 171, and 210. That's the solutions to the congruence equation there. All right. Number 4. We have a matrix A here with a P unknown there. Given that the matrix 2, minus 1, 2 is an eigenvector of A determine the eigenvalue corresponding to this eigenvector. All right. So we know for the eigenvalue, eigenvector thing is that when you multiply A with the eigenvector, it's going to be the same as lambda. It's going to be equal to lambda, which is the eigenvalue here, times the same matrix there. All right. And then we're just going to put the eigenvector here as the x, right? So we're going to have 4, 2, 0, 2, p minus 2, 0, minus 2, 2. Multiply with the eigenvector there. And the lambda here is the eigenvalue we want to find. Yeah, and the eigenvector there. All right. So if you solve linear systems here, you're going to get lambda. So like the top one is just 4 times 2 is 8. 2 times minus 1 is minus 2. 0 times 2 is 0. Equals 2 lambda. And that's it. So you solve for lambda there. So lambda equals 6 divided by 2 equals 3. All right. So that would be the eigenvalue. That's A done. B. Hence show that P equals 3. Well, we just do the second row there. So 2 times 2 is 4. Yeah, I'm just going to do like the same there. And then P times, wait, hang on, that's minus 2 there, not P minus 2. I gotta careful there, gotta be careful. P times minus 1 is minus P, and then minus 2 times 2 is minus 4 equals lambda, which is 3 for that eigenvector, and minus 1. And then we got P here. So 4 cancel with minus 4, and then P is just 3 then. Yeah, so that's the answer for part B. Yeah, as required. Part C. Determine the remaining eigenvalues of A. Well, okay, so we're going to have to solve the determinant, right? So the determinant of so you have A minus lambda I should be 0. Yeah, that's how you solve for eigenvalues. So that's going to be 4 minus lambda, 2, 0, 2, P is already 3, yeah, 3 minus lambda, minus 2, and then 0 minus 2, and 2 minus lambda. Yeah, we want to find the determinant of this whole thing, and put it to 0, yeah, and we find the other values for lambda. That's how you find eigenvalues. So the determinant of this, yeah, the easiest way is probably to take the top row, right, and find the minors. So the top row here, yeah, if we find the minus, taking the top row, so I'm going to do that first. So that's 3 minus lambda times 2 minus lambda, minus 2 times minus 2, so that's minus 4. Yeah, that's the top determinant. And then, oh, this is all times minus 4 as well. Hang on. Yeah, so all of this times minus 4 times, 4 minus lambda. That's just the top bit. And then if we look at this one, we do that minus that, right? So that's going to be plus, or actually minus 2 times, yeah, because I take this value. So the first one that I did, I close these, I close the row and the column, and then I do the minor, yeah, which is this guy, multiply with this guy, yeah. And then second one, I'm going to take this, but you got to put a minus sign here because it's the, it's the cofactor thing. And then you're going to do 2 times that and minus 0 times that, which is just nothing, right? We keep it like that. And then here it's easy for this one because you have 0 here. So no matter what you do here, you're going to multiply 0. So we end with that. And this is 0. Yeah. Now the smart way to do this is to maybe try factorize first, if you can. If you can't, then it's fine. Maybe you just have to expand. Yeah, probably have to expand all of that, right? It's gonna be a little much. Yeah, okay, so 6 minus 5 lambda plus lambda squared minus 4 minus lambda there, and then minus, multiply this all out, I get 8, and then plus 4 lambda, yeah, equals 0. Okay. Yeah, we probably have to do that. So if we simplify that first, we get lambda minus 5 lambda plus 2 times 4 minus lambda there minus 8 plus 4 lambda equals 0. Yeah, we're going to get cubic, right? So minus lambda cubed plus 5 lambda squared minus 2 lambda plus 4 lambda squared minus 20 lambda plus 8 minus 8 plus 4 lambda equals 0. So the 8 cancel there, and then what do we have? We have minus lambda cubed. The lambda squared, we have 9 of them, and then the lambda we have minus 18, yeah, if you collect all the term there. And that's simple because then we know that we can take 1 minus lambda out, and then the rest will be lambda squared, and then minus lambda, 9 lambda here, and plus 18 equals 0. So we know that if we factorize that, we get, what's that, 9 and 2? No, 3 and 6, yeah. And minus 6, like that. Nice, because we know that lambda equals 0, 3, and 6. 3 is one of them already, yeah, because we are told that, wait, yeah, we got the eigenvalue first to be 3, so the other two should be 0 and 6. The remaining eigenvalues, yeah, so part I here, the remaining eigenvalues is 3 and 6. Okay, I just underlined that. And part I, corresponding eigenvectors for these eigenvalues, right? That's also another bunch of work there to do, because we need to put them back in. Yeah, so like for lambda equals 0 here, we're just going to do, again, 4, 2, 0. P was 3, right? Yeah. And 0 minus 2, 2. And then x, y, and z. And then 0, x, y, and z, right? Like that. So here for the first row, we have 2x plus 2y equals 0. For the second row, we have 2x plus 3y minus 2z equals 0. And then the third line, we have minus 2y plus 2z equals 0. So we just solve simultaneous and get some value here. So let's see. If we... Okay, let me just think about that. If we add these two, yeah, so I'm just going to number them, 1, 2, 3. If we add 2 and 3, we get what? So the 2z cancel, yeah, we get 2x plus y equals 0. Well, that's equation 4 maybe. And then we're going to solve between these two, right? Oh, so yeah, this is the same as 4x plus y plus 2y equals 0. So that doesn't help there, so they lead to the same thing. Yeah, which we will take it. So yeah, so that means if we, it's circular here, so if we take z equals 1, right, then y will be equal to, if we z equals 1 in there, and then we get y as 1 as well. If y is 1, then x will be minus 1/2, right? Yeah. See if it works in here. So x is minus 1/2, so that's going to be minus 1. Minus 1, substituting y in, we get minus 1 plus 3, and z is 1, so minus 2. So that works. So this is fine. That could be our eigenvector there. But if we want to simplify it, we multiply everything by 2, so that's by minus 2 maybe. If I multiply everything by minus 2, I get 1 here, minus 2, minus 2. We prefer them to be all integers. So that's one eigenvector for lambda equals 0 here, and we gotta do another one, guys. Right, the same thing here. So I'm gonna take the liberty of copy and pasting here, if you don't mind. Okay. All right, there you go. And then we have 6 left, right? Because we already got 3 there. So this is 6 as well. And then we got to do the same thing again. So 4x plus 2y equals 6x. Yeah. And here, this one is simple because then we can solve it already here that y is equal to, I mean, we could have done it earlier as well. Y equals x, right? This one. Yeah. Let's do another one. 2x plus 3y minus 2z equals 6y. So that would be what? 2x minus 2z equals 3y. And we can sub x as y or y as x. So let's do x, y as x. So this is 2x minus 2z equals 3x, right? So that gives me x equals minus 2z. And let's look at the last one, right? The last one is minus 2y plus 2z equals 6z. And then this is saying that y is just minus 2z, right? Yeah, so that works because x and y are the same. Yeah. So basically, if we put x as 1, y is going to be 1, and z is going to be minus 1/2. That's not nice. So let's put x as 2, y as 2, and z is going to be minus 1. Yeah? Because z is x over minus 2. Right? So that is the vector for lambda equals 6. So we got both eigenvectors already there. That should be the end of part C. Part D. Hence determine a matrix P and a diagonal matrix D such that. All right. Well, this one is actually pretty simple. You just follow the procedure here. To find the matrix P, you need to put all the eigenvalues into some matrix. And we're going to call that matrix D. Yeah. So matrix D is just, well, basically it's just lambda 1, lambda 2, lambda 3, right? And everything else will be 0, 0, 0, like that. So what's it going to be? So I'm just going to go with maybe 0, 3, and 6, right? Just in order there, because the eigenvalues are 0, 3, and 6, yeah, if you remember. And then the next step is to normalize all of the eigenvectors, yeah? So if you normalize all of the eigenvectors, what did we have earlier? So, well, they give us, right? So they give us this. Yeah, if we normalize, well, if you find the I'm just going to put this as V1, yeah, eigenvector. So the modulus V1 here is just going to be the Pythagoras of all of those, which is square root, that's 4 plus 4 is 8, 8 plus 1 is 9, so that's just 3, right? Yeah, so normalize eigenvector V1 cap, let's say, is going to be 1 over 3 and just that thing, yeah, same thing. And let's do V2. So V2, our V2 was 1 minus 2 minus 2, yeah? Wait, this is, I got to put this in order. So, you know what? I'm just going to change this to just lambda V2, yeah? Because it's the second lambda there, is this one. So I need to be, you know, consistent there. And for 0 here is going to be V1 because this is lambda 1. All right, so V1 here, you see the numbers are the same. It's 1, 2, and 2, so it's going to be 3 as well. So V cap 1 is just going to be 1 over 3, 1 minus 2 minus 2, yeah? And then we can do the same for lambda 3 this time, which is 6, right? And that was 2, 2 minus 1 is still the same. Eigenvector 3 is 2, 2 minus 1, right? Yeah. Now we do V with 3 cap again is 1/3 and 2, 2 minus 1. Yeah. Now we put the whole thing into the same vector here. and we call it vector p, right? So vector p will be, I mean, if you put the whole thing, you gotta correspond to the order of lambda here. So lambda 1 first, we're gonna put lambda 1 in the first column, yeah? So lambda 1 in the first column is this guy right here. And as you can see, they all have a factor of a third. So we're gonna put a third out here, and then we just put the things inside in the matrix here. So we get 2, wait, no. 0, this one, yeah, is, hang on. 1 minus 2 minus 2. And then we go to lambda 2, which is for the 3 there. So I put 2 minus 1, 2. And for the lambda 3, I'm going to have 2, 2 minus 1. So that would just be the answer there, because that's what they want, determine matrix P. Yeah? So it's just finding the, the matrix D there. It's just for you to, know the order there. But this is a method, man. You should write matrix D first. Yeah? Because they also ask for matrix D. Sorry, yeah. you gotta also give matrix D here. And matrix D will allow us to find matrix P, actually. So that's it for question 4. Question 5. Part I. A circle C in the complex plane is defined by the locus of points satisfying that. Alright. A, determine a Cartesian equation for C, giving your answer in simplest form. Right. Well, this is modulus of the complex number, right? So you can put that as, so if that's a modulus, then we can do like, because we know that z equals x plus yi, yeah? So we can do the modulus there. So if you simplify that, you get x plus yi minus 3i. I'm just substituting that. 2 and then x plus yi here. Yeah? And then we can do x plus y minus 3i. Yeah? Modulus equals 2 x plus yi. Nothing changed there on the right side. And then we have, if you do modulus, then it's going to be x squared plus y minus 3 squared equals, so you square that, you get 4 here, and this is going to be x squared plus y squared as well. Okay? So if you expand everything, you're going to get a simplified version. So x squared plus y squared minus 6y plus 9 equals 4x squared plus 4y squared. And then I want to simplify that, so I get 3x squared plus 3y squared plus 6y minus 9 equals 0. Yeah? And that is the Cartesian equation. I mean, we can make this into a circular equation if we want to. Do we want to? Yeah. How about we simplify, divide across by 3, we get x squared plus y squared plus 2y minus 3 equals 0, right? And then x squared plus, well, to complete square, we do y plus 1 squared, and then we subtract 1, and we subtract 3, we get minus 4 here equals 0, so we kick that to the other side, we get plus 4 here, and that is just a circular equation. Yeah? So that's it for part A. Part B. On an Argand diagram, shade the region defined by that set, right? Well, this is basically just, if we look at the original equation here, it's just putting the greater than sign instead of an equal sign. So if we look back in our previous derivation here, yeah, maybe we can start from this one because I haven't swapped the sides yet. So we're just going to do x squared plus y squared minus 6y plus 9 greater than, yeah, this is greater than 4x squared plus 4y squared, yeah. And then if you derive further, yeah, you're going to have on the right side, because I did move everything to the right side, but I wrote it on the left side, right? So now we're going to have the right side instead, yeah, to not confuse with the inequality sign. So we have 3x squared plus 3y squared plus 6y minus 9, yeah. And again, if we look back here, we get this to be this, right? Yeah. Well, actually, so it's just going to be x squared plus y plus 9 squared. Well, because this side is basically this side, yeah. So I'm just going to write less than 4, like that. Yeah, and you can try trace back here. So this one is that one, so actually the sign should be this first. and then after you got to the last line here, you will see that it's going to be the same as that. Yeah. So that is saying that this is a circle, of course. And if we draw that on an Argand diagram, of course, so the x will be the real part and the y will be the imaginary part. Yeah. You have a circle at center 0, -1, right? And the radius is 2. So radius 2, we go up by 2, we get to this point. We go to left by 2, so this is -2. We go to right by 2, so this is 2. We go down by 2, so this is -3. If we draw the circle, roughly, that is the circle there. Let's say that is the circle. Let's say that is accurate. Yeah, somewhat accurate. Maybe I can shrink down a bit. Let me resize that. Okay, let's do that. Yeah. So let's say all of this is accurate. And then because you have a less than sign, right? So this is saying you can take any point in the coordinate axis in the space here where the distance from the center to that point must be less than the radius. So that is saying it is the area inside the circle, right? Because the distance from any point xy to the center is less than the radius. That is why it should be inside the circle. So we shade inside here and that should be done, right? For part B. Yeah, IB. Part II, A. The transformation T from the Z plane to the W plane is given by that. Part A describes the geometric effects of T, right? Okay, well, we're just gonna do something with the W there, but I mean, if you use Z equals X plus YI and then you cube this expression, it's probably not going to tell you much about the geometric effects. So when we discuss about the change in geometric effects, it should be about the argument of the Z. So don't forget that we also have the Euler form or the polar form, right? So I prefer Euler form because it's very simple to write like that. So that is saying very holistically that R or the modulus is R units and the argument is theta. So argument is just rotating anticlockwise from the initial line, right? So if we have W equals Z to the 3, well, just put everything there to the power of 3, right? Basically, that's just algebra there. And with the property of laws of indices here, we can do R3 and e to the I3 theta. So basically, you just multiply 3 to this power, you can rearrange to get that. And that is basically saying that the modulus will get enlarged by a factor of 3, and the argument, the modulus will be cubed, but the argument will be multiplied by 3. So that is the geometric effects, yeah? So modulus of Z will be cubed, and the argument, which is the theta of Z, will be multiplied by 3, and that's it. That's the geometric effect. Yeah, that's part A done. Part B. The region I in the Z plane is given by that. On the different Argand diagram, sketch the image of R under T, right? So don't forget we are under T, right? So we're gonna think about the R first, which is this region, and then we're gonna transform R using this transformation equation. Yeah. Well, let's think about the set R here first. Yeah. Well, you have argument in the range of angles. So 0 to pi over 4 is just the range of angles for the argument. Yeah. Now, if we just, go back to some basic here, if you have argument Z, yeah, let's say less than some theta, like that, that's the simplest way. Well, if you have argument Z and nothing else in there, it's just Z, it's not Z minus Z1, right? you're going to start from the origin, which is 0, 0 here. And theta here means that you're going to have half. It's called a half line. Yeah, so it's this line here, where the angle is less than theta. So the angle is less than theta, so you're gonna be looking at this. This is the angle here. Okay? Yeah. Now if you go in the range, right? Let's say you have a theta 1 here on the lower bound and theta 2 on the upper bound. It's gonna be similar. So let's say if I subtend to that angle, it's theta 2. And let's say I have another line here, subtend to the smaller angle, theta 1. Let's do this. Right? So if we want to shade the region, it's just going to be in between these two lines. And, keep going like that. So that means you can take any point within this region to satisfy this inequality of the interset plane, the R region here. Yeah? So now, would it make any difference, just in case here, this is extra supplementary knowledge, would it make any difference if we have, say, argument of z minus z1? Well, it does, because it is effectively just moving. Instead of being at the origin, you're going to move to a particular point, z1. Note that this is the critical value of the argument here, so it's a minus sign here. So instead of that, right, well, let me just group them like this. This is for just argument z, no z1. This is when you have like this, yeah. So let's say that is point z1. You're gonna just move the vertex of where the two lines intersect there to this point z1, and then again you're gonna have an initial line here, and then you have two angles. So this is theta 1, this is say theta 2, and then you shade in between as well. So that is the only difference. Now for this one, it's not that bad, because we have, right, so this is my answer here. We have pi over 4. This is region R first. Yeah, region R in the Z plane. It's not transformation yet. It's just going to be pi over 4. So it's just pi over 4 like this. Yeah, and we shade this. Like that. But sketch the image of R under T. So if we want to sketch this under the transformation of W equals Z cubed there, well, the modulus here isn't affected, because again, if you go back to the answer to part A, we said that the modulus will be cubed, and the argument will be multiplied by 3. But this is about the region, right? So the only thing that is practically affected here is the argument. So instead of that, which is pi over 4, we're going to multiply the argument by 3. As simple as that. So instead of that region, we're going to have 3 pi over 4, which is the second quadrant here. This is 3 pi over 4. And then we shade everything. Yeah, I'm just going to shade like that. Like that. Yeah, and that's it. That's what it is. All right. Because 0 here, yeah, I forgot 0 here is the initial line. Yeah. So I should have had 0 there when I start talking about the principle of half line there. So 0 is there. So it's between 0 to pi over 4, right? It's just that. Okay, so this is just done there. Okay. Next, question 6. Now we have reduction formulae here, by the looks. We have In defined by the integral of cos nx over sin x dx, where n greater than 1. A show that for n greater than equal 1, n in plus 2 equals all that. Right. So it's a better idea to, other than everything else, we start from substituting, instead of n, we have n plus 2 in the integral. So if we use the definition of In here, but we substitute n plus 2 instead, we're going to get cos n plus 2. Of course, it's going to multiply x here as well. We're going to deal with that later. But I'm just starting here, yeah. Well, let's expand x into the argument of the angle there, yeah? So we get nx plus 2x, yeah? Well, what does this look like to you? It's kind of like an additional formula, right? Yeah? So we're going to use cos A plus B to expand that and see what we get. So cos A plus B here is going to be cos A cos B minus sine A sine B, right? And all divided by sine X. We're not done, yeah? Not yet. And then you see, if we also apply the double angle formulae, yeah, for cos 2x and sine 2x, we're gonna have to simplify that. So maybe I'm gonna use, what should I use? I'm gonna use sine, maybe, yeah. Hang on, let me just, yeah, I think I'm gonna use sine, right? Because then we have cos, yeah, okay. Should we? Yeah, we use sine. So I'm gonna just substitute 1 minus 2 sine squared x here, minus sine nx, and then this is just 2 sine x cos x, yeah? Alright. Hope you guys okay with that, because that's just pure math. Okay, and divide by sine x here, yeah? Okay, so how are we going to simplify all that? Right. Well, see, if you expand this all out, yeah, you're going to get the first term to be cos nx divided by sine x, yeah, right? And the second term will be minus 2 cos nx sine squared x over sine x, right? And the last term, yeah, will be minus, well, let's also simplify, yeah? So I'm just going to get 2 sine nx here, and cos x, right? Of course, there's always a dx here, yeah? All right. Now, as you can see, this is already in, right? That's already in there, okay? And let's, this is also simplifiable, so we get that actually, right? Yeah. So if we combine the terms here, right? So this will be in minus, yeah, integral, okay, cos nx sine x plus, there's a 2 here, yeah, plus sine nx cos x dx there. Okay, now this is what? Cos A sine B, right? Cos A sine B plus sine A cos B. This is sine, all of that is just sine nx plus x, yeah? That's just sine nx plus x, right? Sine A cos B, cos A sine B, yep. So if we factorize that, yeah, we get sine of what? N plus 1 and then times x here, as in the argument, right? And if we actually integrate that, right? Integrating sine, we get a minus cos, so that's going to be a plus cos, same angle here, n plus 1 times x, and then divided by the n plus 1. So think of n plus 1 as a k, a constant in front of x. So you need to do a reverse chain rule, bringing it down like that. Well, I think we got it, right? Yeah, that's as required. Yeah, there you go. That's part A done. Part B, hence determine the exact value of that. Right, so, well, this is 5 instead of 1. I mean, look, if it was in I1, right, this is going to be integral of cos 1x. I'm just going to write that so that you know. Yeah, but here we have I5, right, because that's just 5x there. So ignoring the limits for the time being, so we have that. This is what we want to find. But of course, we're not gonna integrate it directly, right? We're gonna use the result from part A. All right. Now, how do we do that? Of course, if we think about how we go from anything to 5, the intermediate I we should get is probably looking at this one. So how are you going to get 5 from in plus 2? That is to substitute n equals 3, right? So if n equals 3, you get I5 here, which is I3 plus 2, right? So that's going to be what? 2 cos n, in this case 3, so 3 plus 1 is 4, so cos 4x divided by 4, yeah, plus I3. That means we need I3, right? That means we need I3. So let's find I3. So how do we find I3? Well, I3 is from I1 plus 2. Yeah? 1 plus 2 there. All right. So it is just substituting n as 1 here to get 3 there using the formula. So this is 2 cos what? N is 1, so this is cos 2x, right? Divided by 2 plus I1. So that means it boils back to I1. We need to find I1, right? And that's fine. So if we found I1, we're going to sub it in here, and this will be subbed in here, and that will be our answer, right? So that's I5 there. This is not what we want. We don't want to do that. All right, so let's find I1 first, yeah? And then we're going to proceed to I5 in order like that. Well, of course, this is integral cos over sine, so it's cot, right? Cot x dx. And because we want all of the integrals here will have the same limits, which is the lower limit pi over 4 and the upper limit pi over 3, yeah? So, but let's integrate cot first. So if you look at the formula sheet, right? Integrate cot. I don't remember that either. So let's look at the pure math. I believe it's ln of ln sine or something. Integrate cot. This is further math. Yeah, here we go. Integrate cot, we get ln absolute sine. Yeah, it's this guy here. Right, so let's get back. Okay, so that's going to be ln sine x because we don't have any k in there, so that's fine. And then you're going to sub in the bounds pi over 4 to pi over 3 in there. Well, let's find that already, right? Because it's going to be separate to the I3 we need to find later. So let's find that. This is going to be, well, ln of sine pi over 3. Sine pi over 3 is root 3 over 2. So that's ln root 3 over 2 is already positive, so we don't need to do that. Minus ln sine pi over 4, which is ln root 2 over 2, right? Yeah? So if we use a log property to merge them, we get ln of root 3 over 2 divided by root 2 over 2. Well, that is just, let me move down again. Yeah. That is just ln 3 over 2, because 2 can cancel here, is 3 over 2 to the power of 1/2, right? And I can put the 1/2 in front like that. So that's I1 under the same limits there. Yeah? And then we can find I3 easily here. It's no problem because let me just squeeze the area a bit here. Let's move that to the next page. Here we go. So then I3 would be, well, yeah, for this one we just put the same limits there, right? So let me put the same limits there. This is just what? Same thing, pi over 4 and pi over 3 there. Yeah, we're just going to calculate that. So, well, 2 cancel, luckily. And then we have cos of 2 pi over 3. Cos 2 pi over 3 is just minus 1 over 2. Yeah. Cos of pi over 4 times 2 would be cos of pi over 2. That is 0, isn't it? cos pi over 2 is 0. So that's just it. That's I3 on its own, and then plus I1, which is 1/2 ln 3 over 2. That's I3. And then we're going to add I3 to this to get I5, right? So this is I5 equals, that's 1/2 there. So it's cos, we'll put the limits in. This is pi over 4 and pi over 3 again. Yeah. So the upper limit is cos of 4 pi over 3. Well, that's that would be minus 1 over 2 as well. And that's going to be minus 1 over 4 because you have to also divide by 2. And then we put pi over 4 in there. We get cos pi over 2. Well, cos pi is minus 1. So that's going to be minus 1 over 2. So that's going to be 1/4 for only that term. I'm just going to do 1/4 already here for that particular term, and then plus I3. So it's going to be plus all this, which will be minus 1 over 2 plus 1/2 ln 3 over 2. So this will be what? Minus 1 over 4 plus 1 over 2 ln 3 over 2. And I think that's it for this one. Yeah. And we are okay because this is A, B, C are all irrational numbers. So we are fine. Yeah. And that's done for number 6. Question 7. What do we have? Aha. Wow. The set of matrices G equals all that. And we have 6 matrices here. With the operation that of matrix multiplication with entries evaluated modulo 2 forms a group. Part A show that B is an element of order 3 in G. Right, so we probably need that first because we're going to probably make use of that later from this part. And we'll see. So B, well, order of element 3, right? So we're just going to square B. Yeah, so B square here is just 1, 1, 1, 0. And we're just going to square that like that. So that's going to give you what? 1 times 1 is 1. So I'm just going to do matrix multiplication, yeah? So that's 1 plus 1 is 2. I'm just going to write first. And then, and of course, we need to find the equivalent for the modulo 2 here. And then the other one will be 1 plus 0 is 1. And bottom left here is 1 plus 0 is 1. And the bottom right is 1 plus 0 is also 1. Well, but if we do modulo 2, that would be equal to, if you divide all the elements by 2 to find the remainder, so this remainder is 0, 1, 1, 1, 1, like that. Yeah, mod 2. Okay? And then if we cube B, yeah, well, as you can see, this is not the identity yet. We gotta keep multiplying B by itself until we get to the identity, and that will be the order of B in G here. All right. So if we multiply that by B again, yeah. So I'm just gonna take the easy number here because we already got that from the modulo there, and then multiply by itself. So what are we gonna get? 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 2. 1 plus 0 is 1. But that is, again, if we apply the modulus here, the remainder is 1, 0, 0, 1. And that is just, again, modulus 2, which is equal to I. So that means the order of B is 3. Okay, that's it. We have shown that. We're going to use the B squared and the B cubed here later, I think. Yeah, so we're going to keep this. We're going to come back to this. B determine the orders of other elements in G. Okay, so yeah, that's going to be a bit tedious there. So we're going to do the same thing for other ones. So I here, I is the identity matrix. So if you multiply by itself, it's already an identity. So this is order 1, right? Because you don't need to square it. It's already an identity there, right? What about for A? Yeah, if you do A squared, what are you getting? So A squared, we do 0, 1, 1, 0, multiply. So This question is going to be long and tedious, yeah? But if you bear with me, you're going to get there. Okay, so how about we apply the modulus as well, right? To boost things up here. So 0 plus 1 is 1. Well, modulus is still 1 there. And then 0 plus 0, this is 0. 1 plus 0 is, oh, hang on. 0 plus 0 is 0. So 1 plus 0 is 1. There's no need to apply the modulus there. This is already order 2, right? Because we square the A and we get to the identity. So this is order 2, right? B is already order 3. Now let's do C. So if we do C squared, yeah, like that. So what do we get? 1 plus 0 is 1. 1 plus 1 is 2. Modulus 2 would be 0 here. And then, is that right? Let me check. Yep. And then 0 plus 0 is 0. And then 0 plus 1 is 1. Ah, so that's also order 2. Seems like we're going to have quite some order 2 here. And then how about D? D squared. Okay. Okay, 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 2. And applying modulus 2, we get 0. 0 plus 1 is 1. So that's order 2. Because that's the identity already. And then E. Yeah. So again, 0 plus 1 is 1. 0 plus 1 again is 1. 0 plus 1 is 1. 1 plus 1 is 2. Modulus 2 is 0. Yeah. That's not the identity yet, so we do again. Okay. And multiply by itself, which is 0, 1, 1, 1. Again, 0 plus 1 is 1. 1 plus 1 is 2. Modulus 2 is 0. 0 plus 0 is 0. 1 plus 0 is 1. So that is the identity. So this is order 3. Now we're done. So we conclude, right? So A, order 2. B, order 3. C, order 2. D, order 2. And E, order 3. Yeah? Right, so we have 2 order 3s and 3 order 2s and 1 order 1. Alright, so that's part B done. Part C. Give a reason why G is not isomorphic to the two of those. Okay, so part I. Why is it not isomorphic to a cyclic group of order 6? Well, okay, so a cyclic group of order 6 means that you would have to have order 6. At least one of the elements should have order 6. Right? And as we can see, none of them have order 6 here. Okay? So that's why it can't be isomorphic to that. None of the elements in G have the order of 6, and that's it, because none of them have order 6, right? So that's why it can't be. Okay, part 2. The group of symmetries of a regular hexagon, right? So we got to find the symmetry order, right, of a regular hexagon first. And now, in order to find that, when it compares to a geometrical shape like a hexagon here, a regular hexagon. So a regular hexagon, right? You need to work out the two things and you add up. First is how many axes of symmetries that you can draw, so that 1/2 is equal to the other. So keep going with that. So 1 there, 2, yeah, 3, 4, 5, 6. Right? So there are 6 axes of symmetry here for the reflective symmetries. And then if you rotate the hexagon, right, I mean, for every 60 degrees, you can rotate it so that it becomes the same orientation. So I'm talking about the rotational order of symmetry here. Yeah, the rotational symmetry of order what in this case. Because you can rotate every 60 degrees to get the same shape. So if you do 360 divided by 60, you get 6. So the rotational symmetry is also order 6. If you add them up, right, now you see that the regular hexagon would have the order of symmetries of 12. Yeah, so regular hexagon would have the order of 12 from 6 plus 6 here. You need to consider both types of symmetry. And G only has order, what was it? It was just order 6, right? Because we have 6 members here. Yeah, okay. So, I mean, 6 members, the maximum order it can be is just 6, right? So that means it can't be, yeah, 6, not 12. So that's why they can't be isomorphic. Okay, so that's part C done. Now this part D, it's going to be a real deal here. The group H of permutations of numbers 1, 2, and 3 contains the following elements, denoted in the 2-line notation. All right, so for those of you who don't understand what these are, right, basically it is saying what we're going to see. So it's just saying how each number 1, 2, 3 is mapped to the next number, and we'll see how that works, right? D determinant isomorphism between the groups G and H. Okay, so we're going to basically match the element, all the elements from the set G here to the group H, yeah. And the easiest thing we can get started here is just to match I to E, because E is the identity element here, right? So that we can do, I match to E. Okay. Now, of course, we match these two because they both have order 1. Okay, it's obvious that the identity matrix here is order 1. Yeah, that's trivial. But how do we know if this is order 1? And that is where you need to know how to do the permutation here in a 2-line notation. Yeah. So if you take matrix E, it's not a matrix actually, it's just 2-line notation. If you look at the matrix E here, and if you start from the first element, 1, because it's 1, 2, 3, all of them is 1, 2, 3 on the top line. So it is saying to you that if you start from number 1, you're going to go to what? Look from the top down here, you're going to go to number 1 next. If you start from number 2, you're going to go to number 2. If you start from number 3, you're going to go to number 3. So all of them bring them back to the same number. And this is exactly the same behavior to the identity matrix in matrix, right? Because when you have the identity matrix, whatever number you multiply with the matrix is going to give you that same matrix. Sorry, matrix, not number. This is the same thing. It's a 2-line permutation here. So 1 brings back to 1, 2 brings back to 2, 3 brings back to 3. That's why we map I to E. All right, so that's fine. Now let's have a look at the other ones, right? Because basically we have to check first if isomorphism exists here, might exist. So I and E are the same order, yeah? And then we have what? The second order, right? Let's write down the second order. That was, let's do the third order first, B and E, yeah? Because there are just 2 of them. So B, so order 3, B, I'm just going to do it like this, yeah? So group G and then group H. So the third order is B and E, right? That's the third order from group G. And then A, C, D will be the second order. A, C, D. And from group H, we don't know yet. We need to work out. Yeah, so we need to work out what are order 3, what are order 2, right? So we work out each one. This is where it gets tedious, guys. Okay, but it's not that bad. So let's look at, I'm just going to copy all the notations there for the sake of explaining here properly. Just bear with me. Okay, so let me just get that image. Alrighty, here we go. Okay, let's do that. Alright. So E is fine, E is order 1 because every number you put in is going to bring you back to the same number. So the length of the cycle is 1. Okay, now what about A? If you start from number 1, yeah? I'm just going to write A here. If you start from number 1, it's going to bring you to number 2. Yeah, just look down, yeah, look down. So if you start from number 1, it's going to bring you to number 2. Now, if you are at number 2, with this permutation operation, it's going to have to bring you to number 3. So number 2, if you use the same A operation here, looking at that, yeah, first line is going to bring you to number 3. So you go number 3 here. And again, if you're at number 3, it's going to bring you to number 1. Well, that seems simple, right? Now, because we repeat already here at number 1, this is the repeated number. The length of the cycle, because if you keep going, you could, but it's going to do 1, 2, 3, 1, 2, 3. Now, the length of the cycle will be the order, right? Will be the order of this notation here. So, and also because this single cycle includes all the members, all of the numbers 1, 2, 3. So we don't need to do other ones. I'll show you that other ones we need to also start from a different number. Yeah. So this is order 3 then, because the length of the cycle is 3. Now let's do B. Again, let's start from number 1. So if we start from number 1, we go to number 3, right? Yeah, this is different now. If we are at number 3, we're going to go to number 2. Just look down. Okay? If we are at number 2, we're going to go back to number 1. Aha. We got all the numbers 1, 2, 3 in a single cycle there, whose length is 3. Then this is also order 3. Yeah? That's done. Right? So far so good. We get order of A and order of B now. They're both order 3 there. Now let's have a look at other ones, like C, D, and F. Yeah. So C. We start from 1. We go to 1. Oh. Well, if we were to conclude here that the order is 1, it would be too soon. We need to start from 2. So where do we go? We go to a different number, 3. If we are at 3, we go to 2. Oh, so that is back to where we started, which is 2. So the actual order of when you see multiple cycles here that you can get from the permutation there, it has to be the lowest common multiple, right? So the length of this is 1, the length of this is 2. So the lowest common multiple should be 2. Alright, wait, I haven't started from number 3. Let's do number 3. So if I do number 3, I'm going to get to 2, and I'm going to be brought back to 3. So that's also, so that's 1, 2, and 2. So the lowest common multiple would be 2. That means the order of E would be 2. Yeah? Okay. That's it. You do it for all other notations there. So if you start from number 1 for D here, you go to number 2. From 2, you go to 1. Well, that's already length 2. But if we start from 2, we go to 1, and then we go back to 2. Well, that's the same. If we go from 3, we go back to 3. And this is again similar to C because the order would be 2 here. All right. And I'm assuming F should be the same because there should be only 2 order 3s and 3 order 2s, right? To match, to have the isomorphism here. So let's do F. if we start from 1, we go to 3, from 3 we go to 1, same, 2 we go to 2, and if we start from 3 we go to 1, 1 go back to 3. So this is also order 2, right? So that means in group H, now we gonna have a table here. In group H, we're gonna have order 3 to be A and B, right? And order 2 to be, what are they? E, D, and F, right? Wait, that's not E, that's C. Sorry, E is already, yeah. C, right? This is C. C, D, and F. All right. Now, our job is not done. We need to map for each, because each of the order is not unique, right? It's like, I mean, this would have been much easier if they only had like 1 order 3, 1 order 2. We can already map them to the other group easily. But we got to choose how do we map B to any of this and E to the other one, and the same to the other part here. And that can be done by, okay, so for matrix, we need to, because this is the operation of matrix multiplication. So we're going to keep multiplying and see what we have. For example, we already know that B squared, yeah, and this is when I refer to the, what I mentioned before, when we do B squared, we get this, right? And that was E, yeah, so B squared is E, yeah? Okay, so B squared is E, so we're gonna check if A squared is also B, kind of the same operation. But A squared in group H here is not multiplying. Okay, so this is in G, right? B squared is E. So in H, is A squared B or B squared A? Well, we're just gonna do a trials and error here. So let's do A squared. Now, what is A squared? A squared is basically you apply the operation 2 times. Yeah? So because A is 1, 2, 3 here and go to 2, 3, 1, right? So we're gonna do A dot A. In notation terms, this is meaning that we're gonna apply this like this. So basically, if we start from number 1 again, we're gonna go through the operation from this first and then this. So if we start from number 1, we apply the operation from this notation. So number 1 will have to go to number 2, right? So I'm just gonna write like this. So number 1, if you do A, yeah, it's gonna give you what? It's gonna give you 2. But because the left part here is also A, so it's like a function. The number 1 on the very left is the input. You input 1 into this permutation operator, it's gonna have to give you 2, because it's just saying here, the top row, if you have 1, you're gonna get 2. Yeah, look from the top, go to the second row. And now when you have 2, if you apply the same operator, because you have A and A here, it's just like composite function, you're gonna have now 3, right? There you go. Yeah, so you have 1, 2, 3 here. And if you apply to, so this is saying if you input 1 to the A squared operator here, you're gonna get 3. Well, we're gonna see for other numbers first and see how they put together. So if you apply number 2 to A, what do you get? Number 2, if you look down here, look at my cursor, you get 3. If you apply number 3 to the same operator here, you get 1. So I'm gonna write 1 here, yeah? And then we're gonna do it to number 3 as well. A, we get 1, right? So 1 here, and looking at number 1, we get 2. There you go. Now, what does this all mean? It means that I can write this A squared as the two-line notation here as well. 1, 2, 3. Now 1 gives me 3, right? So you go from 1, you get 3 by applying the A and the A there. You went from 2, you got 1. You went from 3, you got 2. Isn't this the same as one of them, maybe? Well, if we check, this is the same as the operator B, right? Yeah, the permutation B here. They call it permutation, sorry. So this is equal to B. Aha! Isn't that the same behavior as B squared equals E? Now we have A squared in their terms, which is to apply the permutation twice. You get the permutation B. So we can map now that B will be mapped to A and E will be mapped to B because they have the same behavior. Yeah, they have the same behavior. So that's gonna work, right? We can do that. Okay. Now the other three is gonna be a bit tough, right? For the other three. But bear with me, yeah? We're almost there. At least we got half the marks now, I think. And then how are we gonna map A to any of this and C to any of this, right? So, okay. We're gonna use the conjugation method to check, yeah? So, for example, if we maybe take the B, well, we're gonna take B again because B is quite useful. We know that B squared is E, and we also know that the inverse of B, yeah, we can find the inverse since we have a lot about B. So B inverse is, what's B again? 1, 1, 1, 0. So that's 1 over determinant is minus 1, right? And then times, swapping this and putting minus on that. This is basically just 0, 1, 1, minus 1. And if we apply modulo here, this is going to be 0, 1, 1, 1. Yeah, because it doesn't matter, minus or plus is still modulus. The remainder is 1. Yeah, this is matrix E, yeah, modulus 2, right? So they're the same, remainder. What does that mean? Well, when we want to do conjugation and using matrix B here, so you just basically do the diagonalization, right? So we're going to apply diagonalization using matrix B here for all A, C, and D. Let's see. So we do B, A, B minus 1, like that. Yeah, and see what we get, right? So that's going to be, what's B again? 1, 1, 1, 0. A is 0, 1, 1, 0. That's the identity matrix. That's going to be simple. And then B inverse here is E, right? Yeah. So this will give me the same. Wait, it's not, sorry, this is not identity. Okay, so we do the first two first. We get, yeah, we're going to have to be fast on this one. 1, 1, right? 0, 1. Yeah, the first two gives me that. And this is what? 0, 1 here. 1 plus 1 is 2, so modulus 2 is 0. 0 plus 1 is 1. 0 plus 1 is 1. And this is matrix D, right? Matrix D here. Okay, so let's apply diagonalization to matrix D as well, using the same, yeah, like that. Okay, right. So basically just the same pattern here, but we change the middle one to be the matrix D we just got. Okay, the first two, 1 plus 1 is 2, modulus 2 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, times that, 0 plus 1 is 1, 0 plus 1 is 1, 1, 0 plus 0 is 0, 1, okay, yeah, it should be this. And this is C, right? So when we do diagonalization to D, we get C. Now, you see, we do diagonalization to A, we get D, and then we take this to do it again, we get C. Now we're going to take C to do it again. Yeah? So I'm going to just paste that again. Oops, not that, but this. Yeah. Okay, so the middle one should now be C. Right? So 1 plus 0 is 1, 1 plus 1 is 2, modulus 2 is 0, 1 plus 0 is 1, 1 plus 0 is 1. Yeah? And this is 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 2, modulus 2 is 0. So this is what? A. Aha, so now you're brought back to A. So A, go to D, go to C, and now bring back to A. Now for the group H, right, when we want to consider how the operation of diagonalization here in matrices can be mapped to the permutation, right? Let's take this one. So B, A, B minus 1. Because B is already mapped to A, right? I mean, the matrix B here is already mapped to permutation A, and E is already mapped to B. Yeah? That means if you want to do B, A, B minus 1 here is going to be permutation A times something times permutation A inverse. Let's apply that to permutation C, yeah? So I'm going to write permutation A, C, permutation A inverse. But we also know that matrix B from the group G, when we inverse that matrix B, we got matrix E, where matrix E is also mapped to permutation B. So I'm just saying this is the same as A, C, B, because A inverse in permutation is just B, because matrix B was mapped to matrix E. Sorry, matrix B inverse is the same as matrix E, and we mapped matrix E to permutation B. Yeah, I'm just going to write that maybe here. We map matrix B to permutation A, and we map matrix E to permutation B, and because B inverse equals E, yeah, that means A inverse is going to be equal to B as well. All right. So, but how do we do this, right? How do we do A, C, and A inverse there in terms of permutation? Well, for each one, we can, write a reduced form. The two-line notation is a bit lengthy, yeah? We can reduce from, like A, again, because when you look at A, if we go back to where we found the order of A, you can see that for A, I have 1, 2, 3. We're going to take that. So you start from 1, you go to 2, you're at 2, you go to 3. When you're at 3, you go back to 1. So we write 1, 2, 3. Just the length of the cycle there. So this is 1, 2, 3. It's telling you that if you are at 2, you're going to go to the right to see 3. If you are at 3, you're going to go back to the first one, which is 1. For C, yeah, C is, what was C? So C, we got it. You start from 2, you go to 3. We're just going to write 2, 3. We don't account for this one because when we see 1, we're just going to get 1 from this permutation operator. So we just write 2 to 3 there for C. And for B, let's have a look at B again. So B is 1, 3, 2, yeah? Because that's order 3. So we have 3 numbers there. All right? Yeah, I told you this was going to be a bit tedious. Okay, so if you start from number 1, don't forget you're going to apply from the right. Yeah, you go from the right there. So if you apply this operator, I'm just going to write like this, yeah? B, C, and A. So I'm just going to do B. So if you start from 1, applying the operator B, you're going to go to 3, right? If you're at 3, you apply operator C, you're going to go to 2, because 3 to 2, 2 back to 3, 3 to 2, 2 back to 3, like that. And then you apply this operator. Let me write C here. And then you apply A for the last one. You're at 2, you're going to go to 3, right? You try number 2. We're going to try all numbers, unfortunately. You apply B. Yeah, apply B. You're going to go to 1. You apply C. You're going to go to 1. Because 1 is not in the C here. That means you're going to get the same number when you apply that permutation. And you apply A. You're going to go to 2. Yeah, that. So from 1 to 2 there. Okay. We apply number 3 with operator B, permutation. We're going to get 3 go to 2. From 2, we apply C, we're going to go to 3. From 3, we apply A, we're going to go back to 1. So what is that? If we write 1, 2, 3 as the original number where we started, we're going to get in order 3, 2, 1. And what is that permutation? Yeah, so A, C, A minus 1 here is, this is the same as F. Okay, we're going to do the same. We're going to apply F. Yeah, using this again. A, F, A inverse, which is A, F, B again. Here. Okay, so let's do that. So this is what? A is 1, 2, 3. F. What was F? Well, let's go back and check our mapping here. F was just order 2 again. So it's 1 to 3, right? Because 2 to 2 here is trivial. So it's just 1, 3 there. I'm going to write 1, 3. I mean, you could also write 3, 1. Doesn't matter. It's the same, yeah? Because it's going to give you the same number when you apply it. And B was the same, which was 1, 3, 2. Okay, again. 1, applying operator B, you get 3. Applying operator F now, you get 1, right? Applying operator A, we're going to go from right to left, yeah? We get 2. Number 2, applying operator B, you get 1. Applying operator F, you get 3. Applying operator A, you get 1. 3, applying operator B, you get 2. Applying operator F, you get 2 because 2 is not in the F permutation there. So we get the same number. And then 2 applying operator A, we get 3. So what is this? This is 1, 2, 3 and 2, 1, 3. That is the same as 2, 1, 3 is D, right? So A, F, A inverse is equal to D. Aha. So if we do the diagonalization from B, we're going to get A and D and C. Yeah. So we get A and D and C, like that. We started from what? We started from, where did we start from? We start from C. Yeah, we start from C, and it gave me F, right? And F gave me D. D, little d, I mean, like that. We apply C, we get F. We apply to F, we get D. Okay, so I think if we do again, we're going to go back to C. Just like this one, we go back to A. Yeah? So actually, we should try that because we don't have any matching cycle here yet. I mean, we should try just in case it goes sideways there. So we're going to keep this first. I mean, if my assumption is right, which will bring us back to C, then we can map them correspondingly there. So A to C, D to F, C to D there. Okay, so let's just do that once and for all. So if we do A, F, A inverse, sorry, AD now, AD, A inverse. Yeah, that's going to be the same as ADB. Okay, so that's going to be the same as 1, 2, 3. Because that was, no, sorry. Was it 1, 2, 3? Yeah, A is 1, 2, 3. What is D? Well, looking back in our mapping here, D was 1, 2, right? D was 1, 2. And B was the same as 1, 3, 2. All right. So again, 1, mapping by D first, we get 3 here. Applying permutation D, we get 3 because 3 is not in there. And then 3 by A, we get 1. Number 2, applying B, we get 1. Applying D, we get 2. Yeah. Applying A, we get 3. 3, applying B, we get 2. Applying D, we get 1. Applying A, we get 2. So what is this? 1, 2, 3, 1, 3, 2. This is what? 1, 2, 3, 1, 3, 2. That's C. So we conclude. We get back to where we were. So the same here. Yeah. And we can say then that A is going to be mapped to C, D is going to be mapped to F, and matrix C is going to be mapped to D. So let's conclude that in a table. Yeah. So of course I to E, and we have A, B, C, D, and E, not to scale. Okay, so A to C, B to, we already got that, right? B, we mapped it to what? B, we mapped it to A, and E to B. B, we mapped to A, and E to B here. C to D, and D to F. Just to get these answers, we did all that. It could be tedious, as I told you. Alright, so that's it. That's done for number 7. Number 8. Well, yeah, some calculus now, maybe decent, not tedious. Figure 1 shows a French horn with a detachable bell section. Is the bell section here? Yeah. The shape of the bell section can be modeled by rotating an exponential curve through 360 degrees about the x-axis, where units are centimeters. The model uses the curve shown in figure 2 with equation this. Okay. A show that according to this model, the external surface area of the bell section is given by this. Alright, so let's have a look at the formula sheet. Yep. Let's see, this is the external surface area, so we should look at this formula here because this is also revolution. So we're going to use the top one because we have a normal Cartesian coordinates, right? So we have surface area is 2 pi integral y square root of 1 plus dy by dx all squared and dx. So that's the formula there. Let's get back to the question. Okay. Right. So we have y to be that, so we do dy by dx first. We just get 9 over 2 times 1 over 9 e to the 1 over 9x. And that is just 1/2 e to the 1 over 9x, right? Yeah? So that's fine. So the external surface here is just 2 pi times integral. Y itself is 9 over 2 e to the 1 over 9x. Integral square root of 1 plus this whole thing squared, right? So it's going to be 1 over 4 e to the 2 over 9. Well, if we power that, we're going to get all that multiplied by 2. So basically, we're going to power this, right? And it's just to multiply the power there. So be careful there. So I just got that, yeah? And then this is just dx. Yeah? So if we simplify that, we should get what they want there. Now, because they have 4 here in the square root, so I'm going to do, so 2 can cancel that first. I have 9 pi and then integral e to the 1 over 9x. Well, if I take 1 over 4 out, yeah, if I factor 1 over 4 out of that, I get 4 plus e to the 2 over 9x, yeah, in here. And that will also be the same as, well, 1 over 4, if you take the square root of 1 over 4, you get 1 over 2 outside here, yeah? And everything inside will be the same as they want. There, like that. Well, that means we can do 9 pi over 2 here, and then integral e to the 1 over 9x, square root of 4 plus e to the 2 over 9x dx. And the bounds, right? Well, the bounds will just be the same as 0 to 9. This is not parametric, so we are fine. And that is as required. And k is 9 pi over 2. Okay? Next, part B. Use substitution u equals e to the 1 over 9x to show that blah, blah, blah. All right, fine. We like this because they tell us what to do, right? So we do du by dx first. right? And that is, again, we already got that, right? Oh no, we haven't got that. Okay, it's 1 over 9 e to the 1 over 9x. Or if you like, this is just 1 over 9u, basically. Yeah, we can also do 1 over 9u. Well, yeah, I'm just going to write that first. Yeah, see if we need that. So dx is, yeah, I'm gonna do du over 1 over 9u, like that. But then it's just 9 over u du, right? So the integral of all that, yeah, just the thing they want there, will just be equal to, well, let's deal with the integrand here first. So e to the 1 over 9x is just u there. That's the substitution. And this is square root of 4 plus what? That is basically u squared, right? Because u is e to the 1 over 9x. So e to the power of 2 over 9x will just be u squared. Yeah, so this is basically u squared. Dx is 9 over u du. That's the reason why I prefer 9 over u there rather than 9 over the whole thing, because u cancels here. Okay? Well, looking at the final form here, right, it seems like what we have here doesn't quite match what they want. But if you notice, we have a 9 outside here, which is this 9 here. But this thing is a little out of sync here. So we can tweak the form to be, well, if I put 9 outside and du here, that is basically just this, right? Because we want to put this as the denominator, because they have denominator here, I notice. So that's why I'm going to do this first. And yeah, of course, I can split, right? I can split into 2 terms. See what I have there? So I'm going to split into 9 integral 4 over square root of 4 plus u squared plus 9 integral u squared of that. Yeah, so they're both integrated to du, like that. Now yeah, okay, so we can try do something with this, right? So this one here, maybe we're gonna leave this be first. Let this be for now. Yeah, I noticed that this, you just multiply u in there. So if I multiply u in here, I get 4u squared plus u to the 4, right? So let's try that, right? So this is going to be u cubed divided by square root 4u squared plus u to the 4. Yeah, just like that. All right. Right. Okay. Because I see that there is an 18, right? Okay. So if you multiply that, if you split this into 9 integral 2 over root 4 plus u squared du, and plus another 9 integral 2 over root 4 u squared du. Yeah? Yeah, so I split this into these two, which is possible, right? We are just manipulating here, basically. Just making it the same as what they want. It's kind of like reverse engineering here. And also the same thing up there. Right? And now we're going to do the same for the second term here, because we can do u, and inside the square root down here is going to be the same as the other one, which is 4u squared plus u to the 4. Now do you see that we can combine these and get that first term there? Right? So these two will be combined to 9 integral u to u plus u cubed divided by square root of 4u squared plus u to the 4 du. And the other one, if you multiply the 9 and the 2 there, you get 18 outside, and as they want there. Yep. That must be a good reason they want you to do this, yeah? And yeah, the bounds, right? So we're going to apply the bounds. We're going to change the bounds. So when x equals 9, u equals what? When x equals 9, u equals e. When x equals 0, u equals 1, right? So that means this will be, the lower bound will be 1, the upper bound will be e. The lower bound 1, the upper bound e. Yeah? A and b are constants. Yeah, we got it. Alright, so that's it for part B. Part C. Hence, using algebraic integration, determine according to the model the external surface. Yeah, we just use part B, right, basically. Well, for the first bit, yeah, if we try put them like this is pure math actually, and it's a reverse chain rule. Yeah, to the power of minus 1 over 2. I mean, if you try differentiate this, right? If we try differentiate that by the u, right? You're going to get what? 8u plus 4u cubed. And that is the same as 4 2u plus u cubed, right? You see, it is almost the same as that. Now, if we apply correction factor, multiply everything by a quarter, you're going to get now exactly the same as that, right? Yeah? So actually, let me make it the same as 9 times this. Yeah, we can also do that. So, I mean, yeah, we can just do 9 over 4 here, times 9 over 4, all of them. Yeah, and this is also 9 over 4. To get them the same as this whole thing, right? That means the whole integral will be, yeah, this will be, that's going to cancel, right? So this is 9, no, yeah, it's going to be 9 over 4. The correction factor is 9 over 4. So 9 over 4, yeah, to get it the same as this thing here. You can check the how to do the reverse chain rule if you guys forget, yeah. You just go to the reverse chain rule. I already attached the video in the description. So this is 9 over 4, and then the thing we are differentiating here, because the power is already 1/2, minus 1/2, so we're going to add that power to 1, according to the reverse chain rule formula. It's almost like a reverse power rule, guys. And we're going to divide by, you know, you add that, you get 1/2, right? So divide by 1/2. Yeah? So all that integral will be 9 over 2, 4u squared plus u to the 4 to the power of 1/2. Yeah? That's just the first bit. And the other bit, right, this is 1 over square root of that. Now, we got to look at the formula sheet here, guys. Let's open the formula sheet. Here we go, the formula sheet. Yeah, let's look at these ones. So we have what? 1 over 4, square root of 4 plus u squared. So we're going to write that, 18, 1 over square root of, so 4 is 2 to the 2, yeah, plus u squared du. So which one can we use? Yeah, let's use this one, right? Let's use the ln one. So we're going to use this one, yeah? So that's going to give me 18 ln of x plus square root x squared plus 2 squared, yeah? Like that. Okay? So that's just it. Okay, so we got the two integrals already. We apply the bounds. So we put them together, yeah? The limits here would be upper limit being e, lower limit being 1, right? Yeah, e and 1. Okay, there you go. And then we're going to just substitute that. Don't forget that we also have the k in front of everything being multiplied to the whole integral there, which is 9 pi over 2, right? If you remember, we had it here when we proved it at A, yeah? Okay, so, and that will be the answer there. Just final part now. Well, 9 pi over 2 times the whole lot there. So we're just going to substitute e in. So we get 9 over 2. And then in square root, it's just 4e to the 2 plus e to the 4. Yeah, I'm just going to do 1 substituted in as well. So minus 9 over 2. That's going to be square root 5, right? 4 plus 1 is 5, yeah. And then the ln, yeah. Now the ln is easy because when you do top and bottom here, when you do upper and lower limit, and when you use log property, it's just going to be ln upper limit divided by lower limit. Yeah. So 18 ln. So in there we have e plus square root of e squared plus 4. And then we sub 1 in. We sub 1 in, what do we get? It's 1 here plus square root of 5, like that. Yeah? And because they want 3 significant figures, that means we can use a calculator, right? Just going to use this one here instead. Okay, here we go. And then we have 9 pi over 2 times bracket times bracket, yeah, 9 over 2 times square root 4 e to the 2 plus e to the 4, yeah, minus 9 over 2 times root 5 plus, right, 18 ln fraction. Top one is e to the 1 plus square root of e to the 2 plus 4 divided by 1 plus root 5, yeah, like that. And that should be it. That should be the answer. All right, so 602, 3 significant figure. And that's done, guys, for this question. And that's it for the paper. So I hope that was all useful. If you find the video useful, please give me a like or even subscribe if you think you will find more videos useful. And of course, I plan to do more and more videos on further maths as well. And I'll see you in the next one. Bye.